So we've got another big question to start the show today. And the question is, Damien, why does the concept of learning in machine learning raise philosophical questions about the nature of intelligence, consciousness, and the boundaries between human cognition and artificial algorithms?
I guess one of the reasons is that in machine learning, we discovered a different way to learn than the one we tend to think about when we think about humans. So in machine learning, we have statistical principles that allow us to optimize the learning of a model. So basically, you have optimization principles that allow you to learn from the data. And models are just following that optimization process such that they understand the patterns within the data. It's a very soulless type of learning, and that makes it, I guess, strange if you try to compare that to the way we grow as humans and we learn through experience. But if you look at the way we learn from experience, there's a lot of similarities. We are trying to optimize for some outcomes. For example, we are trying to do things that make us more happy. We are learning from our mistakes. And in a sense, it's very similar to what we try to do when we train models in machine learning.
Yeah, that's interesting. I actually feel that, especially in our everyday sort of, I'm talking about Western practices, when Western society, there is this encouragement to actually try to optimize happiness, which, as you've just highlighted, illustrates, the optimization process that is laid out for a machine learning model. And I actually read a book recently that was called Solve for Happiness, where they were actually looking for the equation that would enable a happy life. So it's almost like we're in a parallel of looking now for opportunities to mechanically optimize our happiness in real life as well, just like machine learning models.
I guess you can say that. And like in machine learning, the important thing to do is to try to find the right metric to optimize. So when you have a problem to solve, you're trying to find the right metrics that would lead the model to learn to predict the right outcomes for the problem you actually have. And in real life, happiness may not actually be the right metric to optimize. So we go through life trying to find the right metrics to optimize, to make sure that we have a more fulfilling life. Sometimes we make mistakes about the right metrics. Sometimes we get it right. It's an experimental process, I guess.
I would say so. Hi, everyone. It's Lauren Hawker Zafer. Welcome back to Redefining AI, the tech podcast. Now, today I've been joined by the machine learning engineer and newsletter author of the AI Edge, and that's Damien Benveniste. Welcome, Damien.
Thank you.
So we've started the flow and the introduction into our forefront topic today, which is machine learning. We're looking at machine learning 101. And I think that we can certainly say with certainty that there's a lot of listeners that have a varying degree of understanding when it comes to machine learning. And I also put myself into the category of being on an ongoing learning journey around machine learning. So maybe we can start with a fundament of looking at it from quite a logical start. People nowadays, I think, especially with the enhanced prominence of machine learning in models per se, they tend to confuse a lot of the terms when they talk about machine learning and the differences in learning. And some people sort of stumble on trying to comprehend it. In your experience, Damien, because you've got 10 years plus experience in machine learning, where are people stumbling? What are they confusing when they talk about machine learning?
Machine learning is a subpart of artificial intelligence, and we tend to call the same thing with those two different names. Artificial intelligence is a field where we are trying to have ways for computers, algorithms to appear intelligent, to make decisions and take actions that look like intelligent ones. Machine learning is a subfield of artificial intelligence where instead of trying to codify intelligence. We're actually trying to learn it from data. Something that I find as a confusion is that, and it's due a lot to the way machine learning is taught in school. In textbooks, you would find a lot of the formalism of machine learning to be very mathematical. And that typical underlying formalism is called statistical learning theory. And this is a set of principles that allow you to have some learning done from the data. And this is a way people tend to educate students about machine learning. And there's a mistake that is typically made to think that machine learning is very much a mathematical science, where in fact, there's a lot that relate to computer science, where you need to implement those principles, those statistical learning principles into algorithms. So there's a big algorithmic part of machine learning. And in practice, machine learning is more of a experimental science than anything else. So we have a lot of principles to have models to learn. But in the end, what we have is people taking some data, taking some models, and trying to get better learning for specific learning tasks. And the field became much more of a set of experimental processes where we're trying to understand how to build better models for some specific learning tasks.
So how would you then encourage people to reteach or reanalyze how they're teaching it? Would you say that it would be more based around trying to experiment with these experimental processes? Or what would you encourage there to try and minimize this misunderstanding?
So the bias that we see in the way it is taught is due to the different people that are teaching that domain. People that are teaching that domains are teachers, professors, researchers that try to push the boundaries of machine learning in terms of the discoveries. But for example, in the industry, a lot of what they teach does not matter as much as other things. And there are things that I wish were taught in school, which would be to understand how to build machine learning systems end to end to make sure you can actually deliver products for users. And that's not something that is taught in school. And it's something that many machine learning engineers take a long time to wrap their head around when they get into working in a company.
Yes, I've also heard that as well. And not to interrupt you, but just to clarify there when you're talking, Damien, so when you're encouraging people to look at being able to understand how to build a machine learning system end to end, what does that mean, build a machine learning system end to end?
So first of all, you start with a business problem. You start with a need from your users, trying to understand what would help them, trying to understand what business metrics would help you qualify or quantify a specific success on the deployment of a new ML-powered product. You need to understand the technical requirements beyond machine learning, meaning that when you need to deploy your models, you need to make sure that they sit on a server. You need to make sure that those servers can handle the request loads. You need to make sure that you have some fail-safe in place. You need to make sure you have some monitoring. You need to make sure that you understand what needs to happen if something breaks. You need to understand who need to work on the different pieces of the problem. There's a lot of skills that go into deploying machine learning systems. Beyond machine learning engineering, there's like ML ops, there's data engineering, there's software engineering. There's obviously some more theoretical aspects that relates to statistics that are sometimes there, but not always. So, there's a lot of things to take into consideration when you build machine learning systems beyond just a model. And it's something that many of the beginners in the field don't really understand, I think.
And then keeping in that as well and trying to understand, real life scenarios, real world problems, we can also see that in understanding the system and the models that you're building, there's a lot of different types of learning and models that can be built. And I think that some of the main ones that a lot of our listeners might have heard are supervised, unsupervised, and now, which is more popular as well, reinforcement learning. So what's the difference between these? And if we were to exemplify those with real world problems, can we give an example of the types of learning that relate to specific problems?
Yeah, so I think we start to go beyond a bit those three categories, especially with generative AI.
Yeah.
We are seeing something slightly different, I believe. But let's start with supervised learning. So supervised learning is the type of learning where you have some input data and you're trying to predict an outcome. So you're trying to basically learn the statistical relationship between some input data, some input variables, and a specific outcome. So for example, if you try to personalize ad placement on a website, you have maybe the browsing history of a user, and you're trying to place a new ad today, right now. And what you need some labels that indicate that the user is likely to click on a specific ad. So you need to have some examples on users clicking on ads. And this is supervised because you have a label that will supervise the learning. You're trying to predict a specific outcome that you have labeled for.
Just one question there. So are we talking about, not only like binary labeling, but like multi-labels? So we've got a possible, 30 labels, 50 labels?
It can be any type of labels. You can try to predict the probability of a user to comment on a post on LinkedIn. Mm-hmm. You can have some labels that relate to how you detect object in an image. You can have some labels that relate to next quarterly profit margin. So those type of labels that you may want to try to, some type of outcomes you're trying to predict, you need a label to educate the model on what that label looks like, statistically speaking, and how it relates to the input data you may have to predict that outcome.
Mm-hmm. Mm-hmm. So how does that differ then to unsupervised?
So unsupervised learning is actually the type of learning where you don't have a label. So there's nothing to supervise the learning. So in supervised learning, you're trying to learn statistical patterns to predict an outcome. In unsupervised learning, you're trying to learn patterns within the data that will help you categorize a bit better the data. For example, clustering algorithms tend to be unsupervised. You just look at data elements, data points, and you're trying to understand how similar those points may be. And you may try to group them together into a cluster. Unsupervised learning also helps you to, by understanding the patterns in the data, help you to change the shape of the data. You can reduce, for example, the dimensionality of your data by crunching it into a different shape than it is originally in.
One question that might be interesting there as well when I'm thinking about the perspective of our listeners is, obviously, both of those have a training set, correct? Supervised and unsupervised. Yes. So what's the differences in the training sets then between supervised and unsupervised?
That's mostly the label. So in supervised learning, you have a training set where you have input set of variables and you have a target, a label. So this is a pair of elements you need to be able to train a supervised learning model. In unsupervised learning, you have a training set that may look like the one of your supervised learning one, but without the label. So you're missing that label. And instead of trying to predict that label, you're trying to find relationship between the data points in the data to try to group them or to shape them in a different format. Also, something that is interesting to know is that in the industry, supervised learning is, I would say, the type of learning that is used 95% of the time. Yeah. Because it's very easy to quantify results, to build some experimental designs where you're going to be able to quantitatively assess a better model and how it relates to your business metrics. It's also maybe more costly in a sense that you may have to spend more money to acquire the label that you are trying to predict. So very often you will need to buy some data, or we need to spend some money to try to acquire the label you're trying to predict. Where in an unsupervised learning setup, it's easier to deal with it because you don't have a label that you need to acquire and you might need to pay for. But it's also less useful. It's also less useful in business settings because clustering or changing the shape of your data, it's not something that has a good business use case.
And where does the modality of the data come into play, Damien? In the East, like if we're talking about maybe images versus text, videos, like, where does the modality come into play when we're looking at these different types of learning? Does it increase complexity? Does it pertain to the use case and the type of learning? Like, where does modality come into play in that?
I guess the data plays a role in maybe the algorithms you're going to use, and also maybe about the engineering pipelines you will need to build to deal with the specific data. When it comes to, let's say, what we call tabular data, where you have a set of variables, let's say, some user variables, age, gender, job title, those are very well-defined categories of variables. We have been very good at building algorithms to predict outcomes on that type of data. This is called tabular data, and we have had very successful models running on that type of data for 20, 30 years. It's something that we know to do very well. When it comes to image or text or audio, this is the type of data that we're being less good at extracting statistical patterns from those to predict interesting outcomes. And with the assumption, with the latest models that we have in neural networks, we were able to actually be more efficient and more performant at extracting the right patterns from this type of data. So now we have very good models that are able to take image as an input, text as an input, and understand the statistics of that type of data to predict an outcome from it. So for example, starting from the 2013, 2014, we've got a set of algorithms that in computer vision that allowed us to be very good at predicting or at labeling, at detecting an object on a specific image. It's something that we were not extremely good at before. Recently, we're being extremely good at generating text because we have better algorithms that allow us to understand the statistics of that type of data. We had models before, but we saw a revolution recently, I would say in 2018, 2019, 2020, in the way to create text from text input, other type of outcomes. And 2013, 2014, 2015, we saw a revolution in computer vision in the way we were able to understand image and predict outcomes from them.
So maybe something that our listeners as well will be asking there, we've sort of transgressed onto like generating text, which comes into the whole generative AI space. And you touched upon the neural networks. We've also got convolutional neural networks, recurrent neural networks that also function in solving different problems. I think reinforcement possibly could be tied in there. I mean, you can tell us if it's not. But when people are thinking about now the generative capabilities of AI and then taking it back to the subset of, machine learning, what can they understand about the machine learning models that are then working in generative AI?
Your question is like, how are the generative AI models different from what we had before?
Yes.
So, yes, the neural networks has been the underlying modeling that led to extremely good generative AI models. You could create generative AI models with other type of algorithms. You don't need you don't have in principle to use neural networks to do so, but it has proven to be much less performant. So the interesting thing about neural networks is what it is. What is it?
That's what I was going to ask. Like, what is it? Because you've got so many terms as well now. I just spoke to someone earlier and they were talking about neural search, and I was like, "Oh, it's neural search." I mean, semantic search, neural search, cognitive search. So, yeah, what's a neural network?
Yeah. So a neural network is a model that is composed of many very simple computational units. If you think about a computational unit, you could think about, a linear regression, for example. A linear regression is a very simple computational unit, something that takes input as, some input data and generate an out, some number from it. So a neural network is composed of many of those computational units. And because you have a lot of flexibility in the way you architect those neural networks, the way you place those computational units in those models, as an engineer, you have more flexibility to architect something very different than what we had before. In previous models, in what I would call traditional machine learning, we have learning algorithms that are not very flexible in the way you construct them. Neural networks, you can really architect their structure. So you can add some different computational units, and you can specialize them to the specific data you input in. For example, convolutional network is a network where you have convolution layers. So you have a convolution, not exactly a convolution, but we call it convolution, that is computed on the image and later in some intermediary results within the network. And those convolutions are very good at understanding the local correlations between the different pixels in an image. And because of that specific computational unit, we were able to understand the statistics of pixels in an image at many different scales in an image. And we were able to have very performant computer vision systems because of it. When you think about language modeling, recurrent network has been a very successful type of architecture where the computational unit, the recurring computational unit, is using previous data and current data to predict the coming data, the future data. So you have this recurring aspect where you're able to reuse what happened in the past to predict with the current input what will happen in the future. So when you think about text, you have words that are ordered. It's really a time series of words. And if you're trying to predict the next word in a sentence, you can use the current word, the one that is just before the word you're trying to predict. But you can also use the words that happened previously in the sentence. And recurring networks have been very good at understanding that.
Just thinking so there's obviously a calculation about the probability of two words coming together. So if we're thinking about the car is driving on the road, then we're looking maybe at the correlation between the car and drive. Is that what you're highlighting as well there?
Yeah, you have a better likeliness to understand what is the next word if you read the whole sentence, basically. So how do you get that whole sentence to be fed into the network such that the network can take into consideration all that information? And more recently, we had the transformer architecture that is not using a recurring computational unit, but more what we call an attention mechanism that is trying to understand the relationship between the words or the different units of data you're feeding it to predict what will be the next unit of data. So in the case of natural language processing, that would be a word or the next sentence.
I mean, obviously, when you're looking at the implementation and the usage of the models in real life scenarios, you've got to consider the performance, like how it's performing. How do you select and evaluate appropriate performance metrics for different type of machine learning tasks?
So it depends on where you work. If you're a researcher, there may be a consensus on the type of metrics that is usually accepted to be the right ones to assess your models on. And when you're trying to build new models, you need to utilize benchmark data to compare your model to the previous ones that has been made developed by other teams. When you're in an industry setting, I think it's a bit different. In my opinion, it really depends on the business problem you're trying to solve. If you have a business problem, then you understand the business metrics you're trying to optimize. So let's say you're trying to optimize quarterly revenue. That's what you're trying to optimize as a company. And well, there are two types of metrics that we usually deal with in machine learning. There's the performance of the model that is measured on production data, and there's a performance of the model that is measured on historical data. And the metrics chosen to assess the models on those two types of data may actually be very different. So what matters is production. When your model is in production, it is when it's generating revenue. When you're trying to understand what is a better model in production, you need to have metrics that relate to your business metrics. So if you're trying to maximize the revenue for the next quarter, most likely you need to have some metrics, what we call online metrics, that assess models based on some type of revenue metrics. So for example, in ads ranking, when you personalize ads, you may have your business metrics, which is to optimize quarterly revenue. And as an online metric, the one you're choosing to run A/B testing between different models, you may want to choose something like model revenue per 1,000 impressions. So how much money did the model generated per impression? And you want to choose a model that generates the most revenue. So this is easy to measure in production because you present an ad to a user and you see if the user click on it or not. But when you run offline experiments, meaning that you use historical data, you don't know what would have happened if you presented another ad than the one that has been presented to the user. So you don't have the full context to actually completely assess the model in the same way.
Interesting.
And typically you need to choose metrics that can be quite different from the one you have in production. So the game is to try to find the right metric that correlate well with your online metrics. So if you have some experimental results that happen when you run some offline experiments, you want similar results happening in online settings. You want to make sure that when you select a model in offline experiments, the same model would be selected if you were to run online experiments. If your metrics don't correlate very well, you would have potentially a suboptimal model selection on your historical data.
Fascinating, Damien. That's really, really good insights. I think that a lot of people will be able to take away and actually integrate into their practices and also their interaction with machine learning. So I've got a million questions that I wanted to ask you, but time is not on our side today. Is there any sort of parting word that you'd like to share with us as we end our conversation?
Well, it's always fun to talk about machine learning. So thank you for inviting me. And maybe we can do that again, in the future.
Definitely. A huge thank you again. And I'd like to thank everyone else that's listening and joining our session today. If you'd like to find out more about AI machine learning and the Insights Engine, then go to learn.squirrel.com. Thank you. Thank you.